All right. Okay. Welcome everyone to our next talk in I2 AI virtual seminar series. Today we are very excited to have Mykel Kochenderfer from Stanford University. Mykel, we are so happy to have you here. Thanks a lot again for accepting our invite. So I'm going to start with a brief introduction. So Mykel is an associate professor of Aeronautics and Astronautics at Stanford University. And he is the director of Stanford Intelligent Systems Laboratory, where they are doing novel research on robust decision-making systems. And prior to joining Stanford, he was a researcher at MIT Lincoln Lab. He received his PhD from University of Edinburgh in 2006, and he got his bachelor's and master's degree from Stanford University. Mykel is also the director of Toyota Center for AI Research and the co-director for Center of AI Safety. And today, he is going to be talking about developing decision-making systems for safety-critical applications. And I also want to add a little bit of personal flavor as well. With me and Mykel, we go way back. So we met when I was doing my PhD at MIT. He was working at Lincoln Labs at that time. And he was writing this amazing book, Decision Making Under Uncertainty. And he kindly invited me to write a chapter on that, which ended up being a part of my PhD thesis. That is, how we know each other. And recently, Mykel also published two books, Algorithms for Optimization, and the newest one, Algorithms for Decision-Making, right? That is the title. And I want to really recommend these books to all the researchers working in artificial intelligence, decision-making, optimization. They are great books, so be sure to check them out. Okay, so without further ado, Mykel, the floor is yours. We are very eager to listen to you.
Thank you so much for the introduction and the invitation to join you today. So much of the focus and advances in AI have involved applications where it has been okay to occasionally make mistakes, like accidentally recommending the wrong movie or misclassifying a dog as a cat. For many years, work on AI has focused on algorithms for making these AI systems better, which is great, and there's still a ways to go. Not too long ago, the focus turned to large data sets with the hope that large data sets will continue to improve the performance of our systems. But now the focus is starting to turn to the challenge of validation. There is a growing realization that maybe the hard part in AI is not really the building of the algorithms or the collecting of the data, but rather is making sure that the system will behave the way we want when deployed in the real world. So after a series of embarrassments, massive research efforts are underway to validate the fairness of AI systems and reducing various forms of bias and discrimination that may be difficult to predict during the design phase of these AI systems that only become apparent when actually deployed in the real world. These are costly mistakes, costly in terms of cost to society, cost to societal trust, cost in terms of the reputation of the companies that use and deploy these systems. I'm an aerospace professor. We try to build highly reliable systems that take people into outer space and fly the 4.5 billion passengers in 2019. That number, of course, went down a bit in 2020, but we're expecting that to recover very quickly. Aerospace systems are incredibly complex, yet an incredibly safe place to be is actually in a metal tube at 30,000 feet. As all the faculty in my department can tell you, the future of aerospace is autonomy, where greater levels of autonomy can enable greater flexibility in the exploration of distant planets or safer, more efficient, more sustainable aviation to transport passengers and goods. So in this talk, I'll discuss some of our work on building and validating complex decision-making systems. As most of you may know, there are different ways to go about modeling decision-making problems. There's the Markov decision process where we capture outcome uncertainty. Then there's the partially observable Markov decision process, or POMDPs, where we capture state uncertainty. And this model is especially relevant in aerospace contexts, where we need to be robust to sensor errors, occlusions, and so forth. There's also reinforcement learning, where we don't know the state transition probabilities or the rewards ahead of time, and we have to interact with the environment in order to understand how it works. POMDPs are especially relevant to safety critical systems where we need to provide robustness to various sources of uncertainty. But unfortunately, many of the algorithms for solving POMDPs are extremely complicated. There were some tools available at the time when I started here at Stanford about 8 years ago. It allowed you to specify problems using text files containing transition probabilities, reward parameters, and so forth. But for many of the problems of interest, even just the state transition probabilities would be too large to fit in a file. So what we wanted to do, and this is what we did with my first PhD students, was to create a library that would allow a non-expert user to specify their problems programmatically. We created a library that would make this really easy for people to specify their problems and then try out different solution algorithms. And we wanted something that would be fast and easy to use, as well as usable for teaching. So this resulted in POMDPs.jl, which is written in the divine language, which is Julia. It's interactive, it's fast, it's typed, and we can write for loops and do branching without a huge performance penalty. And I really wanted to make the idea of POMDPs broadly available to the general engineering audience. And Kemal mentioned the book Decision Making Under Uncertainty that came out in 2015. I wanted to reduce the heavy notation that was traditionally used with POMDPs and make it more accessible. And I was really happy with that book. But then I worked together with my PhD student, Tim Wheeler, and friend Kyle Ray to greatly expand that book, go way deeper, and also capture all of the great innovations since 2015 or so. I also added, together with Tim and Kyle, many more examples, and we included Julia in place of pseudocode so that you can actually go and execute the algorithms that are in the book. So partially inspired by the classic book Numerical Recipes in C, but in a higher level language. So underlying many of these systems, as well as the validation of these systems, at its core is optimization. And so also together with my former PhD student, Tim Wheeler, we wrote a book called Algorithms for Optimization, which provides an extremely broad overview of the field, ranging from multidisciplinary design optimization, surrogate modeling, multi-objective optimization, both convex, non-convex optimization, and so forth. So a major success story of a POMDP approach to modeling decision problems is ACAS-X, the next generation aircraft collision avoidance system. It grew out of our research back when I was at MIT Lincoln Laboratory. It started out as a concept on a whiteboard in 2007, and we were able to sketch out much of the details of decision-making logic over a couple of years, resulting in a technical report in 2011. So you can find a PDF of it online. But it actually wasn't until 2018, after tremendous effort by folks at the FAA, Lincoln Laboratory, Johns Hopkins Applied Physics Laboratory, the MITRE Corporation, and others, that it became an international standard, RTCA DO-385. That's the version for manned aircraft. The version for unmanned aircraft was accepted as a standard just in 2020. So you might be wondering, why did it take so long to have it accepted as an international standard, despite teams working on it spanning multiple organizations? Well, this is a system that we don't want to mess up, and it's a system that everyone in the world needs to agree upon. So just going back a little bit in history, there has been quite a bit of interest in collision avoidance long before 2007. In fact, in 1956, there was a mid-air collision over the Grand Canyon involving United Airlines and TWA. There were 128 fatalities, a press frenzy, congressional hearings, and ultimately the establishment of the FAA in 1958. Even with these, ground-based radars and the introduction of air traffic control, the modern air traffic control system, there were still these mid-air collisions. The one on the left was actually captured on film as it happened in 1978. There were 144 fatalities, and it spurred additional interest in developing a system that was later called TCAS, the Traffic Alert and Collision Avoidance System. It wasn't until after the 1986 collision over Cerritos, California, just a few miles from Disneyland, that Congress decided to put laws into effect that would mandate the equipage of TCAS in the United States. By about the year 2000, the rest of the world had followed suit. So TCAS is composed of a surveillance system that detects and tracks intruders. It passes these sensor measurements onto the advisory logic that decides whether to provide an alert to the pilots, which maneuver to advise. And these resolution advisories are passed on to the cockpit. The advisory logic contains a bunch of if-then rules, different parameters, and so forth. So I'd like you to try to guess as to how many pages of pseudocode is required for specifying the logic. So I'm a third-generation pilot. My dad ran a flight school, actually just on the other side of the hills over there. And his dad ran a flight school. But even so, I did not properly appreciate the complexity of getting this logic right. So I'll tell you the answer here. This is a screenshot of volume 1 of RTCA DO 185B, the TCAS standard. The first volume has 1,799 pages and 440 of it is pseudocode. I got to know many of the brilliant people who worked on this system. Many of them had worked on it since before I was born. It placed a huge burden on the designers to anticipate all the different edge cases and decide on a way to resolve them. It required a massive engineering effort. So consequently, TCAS has been a major success story. Since TCAS was mandated in the United States on large aircraft, there have been 0 mid-air collisions involving TCAS. Smaller general aviation aircraft, like the ones that I used to fly, little Cessna 152s, those aren't equipped with TCAS, and there's a mid-air collision every month or so, just in the United States. When we were designing the next generation of this system, I was thinking about what makes this problem really hard. And it really boils down to these 3 reasons. We have state uncertainty because our sensors are imperfect. We have dynamic uncertainty. There's quite a bit of variability in pilot behavior. We can't perfectly predict where the future trajectories of the aircraft will be. And we have multiple competing objectives. The system has to carefully balance between both safety and operational considerations. If the system's alerting all the time, then no one's going to follow it, and you wouldn't get the safety benefit. So it turns out that the POMDP framework just directly addresses these 3 major challenges just head on. And so what we did was we framed this as a POMDP and then applied dynamic programming to find the optimal solution. And I'm going to show you, I won't walk you through those algorithms. You can read about it in the book, or you can take one of Kemal's classes. But I want to show you the result of our very first experiment because it's pretty interesting. Our first experiment back in 2007 or so. So this is the policy that we get. And it roughly corresponds to our intuition. The horizontal axis is the time to potential collision. Vertical axis is our altitude relative to the intruder. I love this plot so much. It's actually included in the original decision-making under uncertainty book. So it's interesting for a few reasons. Okay, so if we're above the intruder, we want to climb. If we're below them, we want to descend. But you'll notice a couple kind of weird things here. One is this little notch on the left-hand side here. And actually, at first I thought it was a bug. So we filled it in, reran a bunch of simulations, and it actually did worse. So why is that? Well, it boils down to three reasons. It lowers the alert rate, right? Because if you're roughly co-altitude, it's possible that the intruder will go above us or below us just on their own, because embedded in this model that we're trying to solve is stochasticity. Okay, so it lowers the alert rate. The second reason is it helps prevent you from committing to a direction that you would later have to reverse. Okay, so it lowers the reversal rate, which brings us to the third reason, which is it's just a lot safer. Because when you do a reversal, it eats up a lot of time as the aircraft are converging upon each other. So this is actually what we wanted. There's another kind of weird feature here, and it caused a lot of worry at first, but I can explain it. So you'll notice that if the intruder shows up, you haven't seen the intruder before, but they pop up in front of you, and you're 5 seconds to potential collision. It doesn't alert at all. So why is that? Well, embedded in our first experiment, our first model of the problem, we wanted to carry over as many of the assumptions from TCAS, just so that we would have a baseline. So TCAS makes the assumption that the pilot takes exactly 5 seconds to respond, followed by a quarter G maneuver to comply with the advisory. So the POMDP captures this, and dynamic programming is infinitely intelligent, and it knows that if it produces an alert, it will just accumulate the cost of that alert without actually bringing any benefit in terms of improved safety. So that's really not really what we want, right? In reality, we have some hope that the pilot will respond immediately or in 1 second or whatever, and we're uncertain, so we should use a probability model for that and bring it in. That's easy to do with the POMDP, and we can resolve, and it pushes the alerting region over to the right. So we ran a million stressing encounters with this very simple initial model. It was also just 2D head-on and so forth, so very stressing, not really meant to be representative of the actual airspace. But what we can see is that the NMAC rate, so the near mid-air collision rate, drops by a factor of 50. While alerting only 70% of the time, it does strengthen more often. So a strengthening is if you provide an initial 1,500 foot per minute climb, you can strengthen it to 2,500 feet per minute. And the reversal rate is a lot smaller. So overall, this looks really good. But the FAA could look at this and say, well, I would like the strengthening rate to be closer to that of TCAS. Well, what do we have to do? Well, we just increase the cost of strengthening. Okay, and then we rerun the dynamic programming. Okay, so things have come a long way from that original experiment. This slide captures the different flavors of ACAS-X. There's ACAS-XA for large manned aircraft, ACAS-XU for large unmanned aircraft. There's ACAS-SXU for small unmanned aircraft. There's XR for rotorcraft and advanced air mobility systems and so forth. And they all have to interoperate with each other. So this presents a number of verification and validation challenges. And I'm very excited about that. So there are a number of different validation tasks. Monte Carlo modeling and simulation analyses can go a long way in validating a system. We're interested, of course, in estimating the probability of failure. This is difficult for a number of reasons. One is we need to run this in simulation, and we need a good model of the environment that we can trust. This model absolutely must be independent of the model used for optimizing the logic. For ACAS-X, we used a relatively simple POMDP model, but we used a much higher fidelity model for the validation of the resulting policy. We collected 9 months of radar data from all of the FAA and Department of Defense radars and built up a Bayesian network to capture all the various statistical correlations between the various variables. Then we can sample from that many times to arrive at a probability of collision. Since our systems are very safe, we naturally need many simulations in order to arrive at a good failure probability estimate. We can take advantage of importance sampling and the cross-entropy method to reduce the variance of our estimates, but we still need quite a bit of computation. So during the validation process of ACAS-X, we ran tens of billions of simulations, and we were one of the primary users of the Lincoln Laboratory supercomputing grid. At design time, we also want to be able to identify the most likely failure modes. But we, of course, in order to do this, need a probabilistic model of the environment in order to measure likelihood. Searching the space of possible scenarios is also challenging because there are many variables and the scenarios extend across time. I'll dig into this shortly. When we throw massive computing power at simulating many simulations, we will, of course, find failures, at least for aircraft collision avoidance systems, and this goes for automating driving as well. No system will be perfectly safe, and we have to accept that. If our simulations discover hundreds of failure scenarios, we'd like to categorize them into failure modes that are interpretable. Then we can decide what to do with those failure modes. Okay, so going back to the idea of finding the most likely failure, this is really an optimization problem. We want to maximize the probability of a trajectory subject to failure. The key insight here is that this optimization problem can be framed actually as a POMDP. And this is how we set up the problem. We call this adaptive stress testing. We need a simulator that captures the environment and the system under test. The system under test could be TCAS, it could be ACAS-X, it could be some automotive system or whatever. But that system can just be a complete black box. So for an example, with TCAS, we just took the Honeywell compiled C code. We did not need to peer into the source code at all. We just needed to be able to run it. And then the simulation produces an observation and reward. A key part here is having the reward related to the log probability of the state transition. So you'll recall that in MDPs and POMDPs, you try to maximize the expected sum or expected discounted sum of rewards. And if you're maximizing the sum of log probabilities, you're actually maximizing the likelihood of a trajectory. And then we can plug in any reinforcement learner we want. We could use Monte Carlo tree search or deep reinforcement learning or whatever. My students have explored different schemes for this. The learner outputs an action that perturbs the random variables in the environment. And you continue with this loop, and the output will hopefully be something close to the most likely failure path. Of course, this is all sampling based, so there are no formal guarantees here, but we've applied it to the validation of ACAS-X, and we do get useful, interesting failures. And this failure comes from a very early prototype of ACAS-X. And you get the full trajectories. So we can play this back in simulation and see what's going on. Maybe that suggests changing parameters in the Kalman filter or changing parameters in the reward function or whatever. So you want to understand the most likely failures during design time. So you can do something with that. We've also applied this to automated driving. This is a little video from the Carla simulator. It's modeling a perceptual system, a computer vision system. You can see a bounding box around the pedestrian here. And there's a control system on board the vehicle. So we wanted to see if we could use that same code and find the most likely failure. And it turns out that we get this. And I think we can all agree that this is profoundly uninteresting, right? The pedestrian basically runs at our vehicle. There's nothing we can really do about it. So what my students did was they incorporated into the adaptive stress testing framework the RSS system. RSS came from Mobileye, which was later acquired by Intel. And we incorporated that into the reward function to focus on finding problems where we are not at fault. So RSS tells you, assigns blame in automotive contexts. So we end up getting something that's a lot more interesting. So you can see the bounding box jumping around a bit, and perhaps our vehicle is driving a little bit more aggressively than we would like. And this turns out to be the most likely failure. So this will suggest maybe we need to tune some parameters in the Kalman filter or change some of the parameters in our driving. Okay, so adaptive stress testing is a sampling-based method, as I mentioned, but regardless of whether we use Monte Carlo tree search or reinforcement learning in our optimization loop, we don't get any formal guarantees. We've explored the use of formal methods for verifications, which do allow us to make formal guarantees about performance, at least guarantees with respect to some model. Okay. A collaboration with others in the Stanford CS department a few years ago led to the creation of the ReLUplex algorithm, which is a sound and complete algorithm for verifying properties of neural networks. The properties are defined over an actual continuum of inputs, so infinitely many different inputs. And so there's no way to exhaustively enumerate all of them and check whether the outputs adhere to some property. It actually involves formally reasoning about the individual weights in the network and arriving at a proof that the property holds, or if it doesn't, it'll produce a counterexample. And we can use verification algorithms to support reachability analysis, as I'll discuss shortly. We may want to prove that if we follow a policy represented by a neural network, that it is impossible to enter an unsafe set. We have also done work on probabilistic model checking, where instead of determining whether a property holds or not, we can prove that a property holds with that at least some probability. So what initiated our work on ReLUplex was some work done by my former student, Kyle Julian, who is actually now at Wing. We were interested in seeing whether we could compress policies for unmanned aircraft collision avoidance represented as numerical lookup tables. So that the ACAS-X standard, the complexity is represented by lookup tables, not neural networks, but we wanted to just explore what would happen here. So what I'm showing here is just a notional policy that was generated using an open source implementation of a very simple toy collision avoidance problem, not the original ACAS-X system. So this table occupied 1.22 gigabytes, and it was able to fit, and Kyle was able to fit a neural network to the action value function, which resulted in a policy that looks like what you see here on the right. So instead of 1.22 gigabytes, the weights in the neural network occupy only 103 kilobytes, which is, quite an impressive compression ratio. He didn't spend too long training this network, and as you can see, the decision boundaries are not perfect, but it looks roughly sensible. But what was surprising about this research, which you can read about in the journal article below, is that it performs super well when evaluated on a variety of metrics using Monte Carlo simulation. So, of course, one should be very wary of using a neural network for a safety critical system. And the reason for that is that neural networks can produce unreasonable outputs for what appear to be very benign inputs, as we've seen in the literature on adversarial examples on image classification. So we wanted to see whether there was some kind of formal statement that we can make about the properties of these neural networks. So one property we might want to prove is that regions where we expect one type of advisory provide that advisory consistently over the infinitely many points that compose that region. So here in this plot, it looks like we consistently produce a descend 1500 advisory in that top rectangle. But of course, the image we see is produced only by a finite sampling of that rectangle. But ReLUplex is able to verify that this property holds. There are plenty of other kinds of properties that we might also like to prove. We found that proving properties like these can take an order of minutes. That is for networks for the size relevant to collision avoidance. Unfortunately, ReLUplex does not scale up to networks of the size used for solving image classification tasks. But we've been making, we and many other researchers around the world have been making quite a bit of progress since the 2017 paper on ReLUplex. We also, together with Clark Barrett's lab and Guy Katz, released the Marabou framework, which is a more recent implementation of ReLUplex. So it scales to larger networks now, but we still can't prove properties about networks with hundreds of thousands of units. So many other labs around the world have also made progress in the past few years in developing verification algorithms. My former postdoc, Changlu Liu, who's now a professor at CMU, she went through and surveyed all of these different neural verification algorithms, and we produced a Julia library and a rather long survey article. These algorithms combine insights from reachability analysis, primal and dual optimization, and search algorithms. Some of these algorithms sacrifice completeness in order to achieve greater levels of scalability. Those generally require over approximations. So I'll just show you real quick how you might be able to incorporate one of these verification tools to support reachability analysis. So let's say we start off with a slice of this neural network policy. We discretize that space into a finite set of these grid cells. And so let's just focus on this one in red. So here it looks like there's, in that red cell, it's either descend 1500 or climb 1500. We can actually call ReLUplex or whatever and actually prove that those are the only two advisories in that region. So we can then use an over approximation of the dynamics and say, oh, we're guaranteed to be in one of those two cells if we issue a descend, or one of those two cells if we issue a climb. And then we can prove from those resulting cells which advisories are available, and then again use an over approximation of the dynamics to see what states are reachable. So we can run this and we can see if, given some initial conditions, maybe that we start at least 40 seconds to potential collision, that if we follow our advisories from the neural network, that we will never have a collision. We've done this for horizontal collision avoidance systems as well, and there's some neat plots that Kyle made here. And we can see that the space around the intruder is unreachable. So my student, Chelsea Sidrain, has been leading some work on symbolic methods for closed-loop reachability analysis that does not require discretization and may be more scalable to larger problems. Together with a former postdoc of mine, they created a tool that provides relational piecewise linear over-approximations of multidimensional functions. This over-approximation can be used to represent the dynamics of the system. The example here is of the really simple inverted pendulum problem. So we start in some initial region designated by that square at the bottom left of the state space. What we would like to determine is what region we might end up in after 10 time steps. One approach, of course, is to run a bunch of simulations with our neural network policy in the loop, and we see that we end up in that orange region. Of course, we don't have any guarantees, but that's roughly where we will end up. Another approach is to use a mixed integer problem formulation and use an off-the-shelf solver to determine the rectangle we will be in after each step, and then just iterate a few times. So this approach is called concrete reachability because we make the reachable set concrete after each step. Another approach is to use what is called symbolic reachability, which results in a larger mixed integer program that takes longer to solve, but it can result in a tighter bound for where the pendulum might be after 10 steps. I'll briefly mention some other work that Kyle Julian did together with former student Richie Lee, who's now at NASA, on TaxiNet. So this is part of the DARPA Shared Autonomy program. So we have this neural network that was trained to follow the runway center line. And this was done in the X-plane simulator so that we could, run, thousands of these simulations. And the question that we wanted to answer is, can small perturbations to the image make the aircraft leave the runway or the taxiway? So maybe we allow, 3% perturbation on the image. So this is how it works. We take the image, we downsample it, turn it to grayscale. That image becomes the input to a neural network. The neural network outputs cross-track error and heading error. And then based on those two errors, we have a very simple linear controller that steers the aircraft. And this is a closed loop system. Okay. And so to start off with, we ran a bunch of simulations with a bunch of initial conditions, different lighting conditions, because we know that sometimes computer vision algorithms or computer vision networks can be sensitive to lighting conditions. But in our simulations, it all appeared like very reliable, very, very reliable. This is just a finite sampling that I'm showing here. So we wanted to see what would happen if we allowed 3% perturbation of the image input to the system and see if those perturbed images could get them to just the left side of the runway. So we actually make a series of calls out to Marabou, the newer ReLUplex implementation, to find the perturbation that would lead to the most extreme left steering command. And as I run this video, you can see the trajectory evolve on the bottom left, together with the true image, the downsampled image, and the perturbed image. The perturbed image looks relatively benign. As you can see, we can get the aircraft pretty far to the left side of the runway, but there comes a point when the loud perturbation, the aircraft just corrects itself. So this kind of approach failed to find a failure trajectory. So a key insight that we had was to combine this idea with adaptive stress testing. So instead of just constraining ourselves to just extreme left steering, we wanted to allow for both extreme left and right steering. And adaptive stress testing could find the right sequence of image perturbations that could result in a failure. And in these series of plots, you can see the result of our Monte Carlo tree search tree, with a node shown in red, and the blue line shows the failure path. So with 2% perturbation, there's actually not really it couldn't find a failure. But with 3% perturbation, it figured out that if you steer the aircraft over to the left and then produce an extreme right maneuver, it will end up in a position in the state space that's very far from the training set. And it will actually blast through the other side of the runway. So this was super cool. I was really excited by this result. And instead of just extreme left and right perturbations, we also looked at using potentially smaller amounts of perturbation, but in the right sequence, with the idea that smaller amounts of perturbation are more likely. I'd like to quickly mention some work that my former student Maxime Bouton worked on related to probabilistic model checking. The idea in probabilistic model checking is that you check whether some property holds with some probability. This property can be specified in some languages like STL or LTL, linear temporal logic. There are many great tools for probabilistic model checking, but they generally assume full state observability. There was one exception that was elaborated on in a 2017 paper that involved partial observability, but the approach they took was to discretize the belief space and turn it into a fully observed problem. So, of course, this is not going to scale very well at all. So what Maxime did was to interface with a library that converts LTL formulas into finite state machines. Then he wrote a teeny little bit of Julia code that combines the finite state machine with the POMDP representation of the problem. And then that allowed us to use the POMDPs.jl package to solve for policies that maximize the probability of these LTL formulas. And it also tells us the probability of satisfaction, and you can find an implementation of this online. Led by my student Sydney Katz, we've also started to look at using probabilistic model checking to provide probabilistic safety guarantees when using a neural network controller. So instead of using a uniform discretization of the state space, like what Kyle did for his reachability analysis, she developed an adaptive discretization method that minimizes the volume of the input space covered by cells with multiple different actions recommended by the neural network policy. So the number of actions available from a cell can be determined by calls to Marabou. We can then use this over approximation to arrive at failure probability estimates from different points in the state space. We have to be careful about how we do this, since we want to preserve the formal guarantee that we want from a probabilistic model checker. That is, that the probability of failure is guaranteed to not exceed some threshold. Anyway, Sydney came up with some methods to provide various variable levels of refinement of these probabilistic guarantees, inspired by some state abstraction methods discussed in the reinforcement learning literature. With additional computation time, we can afford to prove that we are safe in certain areas of the state space that we wouldn't have been able to before. All right, so just to wrap up here, when we are building safety critical systems, or actually any kind of decision making or decision support system, we want to make sure that the system is robust to the various sources of uncertainty inherent in the real world. POMDPs they're just one way to frame this kind of uncertainty, and we can use a variety of different optimization algorithms for solving them or approximating their solutions. This optimization can improve robustness in ways that are sometimes counterintuitive. We saw that with the aircraft collision avoidance example. And this is where these kinds of techniques can bring quite a bit of value. But proper validation of the system is absolutely critical. Establishing trust in safety critical systems requires a variety of approaches, including identifying and categorizing different failure modes. That there really is no one silver bullet here. So formal methods have difficulty scaling to problems of interest. They also generally have to make very restrictive assumptions in their models in order to be able to prove anything. And sampling-based approaches on their own, they can have difficulty finding relevant failures. There are some very exciting applications of formal methods that can support the validation of controllers represented by neural networks. We'll have to see how far we can take them. These are still very much the early days. But I'll wrap up here. You can find my email at the bottom of the slide as well as a link to the webpage of the Stanford Intelligent Systems Laboratory. So I think I think the viewers can submit questions.
Yes. Thanks a lot, Mykel. First of all, it was a great talk, and I can also see people cheering up on YouTube. Sorry, we cannot, have clappings in here, but everybody was happy. Thank you. Thanks a lot for the talk. Yeah, let's start with questions. We have a couple of questions on YouTube. I will start asking them first. So I believe most of the questions are actually about this adaptive stress testing mechanism, like how does it actually work? So for example, one of the questions is, in the automotive case, the car case, do you define failure as a crash or being close to a crash? Like, for example, a false alert, would that be counted as a failure? So that's one of the questions.
Ooh, that's a great question. So generally for both our aircraft analyses and vehicle analyses, we generally have a little bit of bubble around the vehicles, just to simplify the modeling. We have also used like wireframe models and so forth, but for the most part, we're looking at things like near midair collisions for aircraft or other metrics like hard brakes in vehicles. So nothing about adaptive stress testing requires like any kind of physical proximity. You can actually define the failures as in terms of any kind of property of interest. So if you want like a unnecessary alert to count as a failure, then you just incorporate that appropriately into your reward function.
I see. Okay, thanks. Well, the next question is, so in the failure identification or the stress testing framework, what are the actions taken by the reinforcement learning algorithm? Yeah,
so it's a little bit backwards and a little bit strange because we're used to using reinforcement learning to find policies, to make the decisions for our system. But we don't do that. But we aren't making decisions for our system because we already have our system. That's what we want to validate. So it kind of turns reinforcement learning on its head. So in adaptive stress testing, the system gets folded into the environment, and the actions that are being taken by the reinforcement learner in adaptive stress testing are actually the state transitions. So you can transition to a variety of different next states, but there's a penalty for selecting next states that are less likely, where you don't get as much of a reward. So adaptive stress testing kind of steers the environment to lead to a failure.
Right, I see. Another question, for the ReLUplex algorithm, are there any other limitations of this algorithm other than the size of the network it analyzes? I believe,
Yeah, so the scalability, fundamentally verifying a neural network is an NP-hard problem. ReLUplex is sound and complete, but in the worst case, it's going to require an exponential amount of time. So the thing that takes a lot of time in ReLUplex is basically case splitting. And that case splitting involves reasoning about whether different nodes in the neural network are activated or not while in the designated input region. So it tends to, if you have very large networks, then that can cause a problem. There's some impact on like the number of layers, the number of units, the connectivity, and so forth.
I see.
And we're still trying to get our heads wrapped around what really matters in terms of scalability for these models.
For these models. I see. So that's like an active topic.
Yeah, that's an active topic.
Okay, more questions. So one question is on, so after we do this, for example, reachability analysis, and if the system is diverging, how do we decide if that is because of the system dynamics or is it because of the neural network controller? Like, can we tell which one is broken?
Good question. So it could also be that neither is broken. And okay. It's just that the over-approximation that we're using is too coarse. So it's since we're using an over-approximation here for the reachability analysis, the analysis could be overly conservative. You can reduce the conservativeness by increasing the resolution of the grid, but that will be at the expense of additional computation. So for the most part, we've been operating under the assumption that, if there's a failure, then it's the fault of the neural network. But it could be that, as a person is asking here, it could be that, our model of the environment is too broad. Yes. So I guess one thing that we could do is look at sensitivity studies of the transition model. A major part of the validation of ACAS-X involved a bunch of flight tests. And during those flight tests, we collected a massive amount of data. And from that data, we could validate our error models, the transition models, and so forth. And if it's looking that from that data that our original models were too conservative, then maybe we could narrow things down.
I see. Okay. Yeah. Thanks for the answer. Okay, I've got a few more questions. So I will try to end everything by 5 minutes to try to respect the time limits. Okay, so one of the questions is this is about the famous crash in 2002. Yeah. I'm sure sorry. Yeah. So the AGL plane crashed with a Russian aircraft. Even though TCAS alerted both pilots to take appropriate actions, the crash still happened due to shortcomings of the ATC and some language barriers. So the question is, does this newly accepted ACAS-X have the same type of problem, or what would it do in a situation like this?
That's a great question. So part of the motivation behind taking this POMDP approach to collision avoidance is to better capture the variability in pilot responses. Okay, so what happened in that situation was an air traffic controller instructed the pilots on the air traffic controller instructed the Russian pilots to do the opposite of TCAS unknowingly. And the pilots decided to follow the advice of the air traffic controller. And then they ended up colliding with each other. Yeah, sure, yeah. So we wanted our system to be more robust to variability in the behavior of the other pilots. And so what ACAS-X would do in this situation is on the DHL aircraft, reverse their original descent to a climb. So TCAS had the ability to do reversals like this, but there was one line of code in the original specification that inhibited reversals in exactly this kind of situation. So as you can imagine, together with the FAA and the international civil aviation community, we played back all sorts of variations of the Uberling incident to indeed confirm that ACAS-X provides robustness to this kind of situation.
Nice.
So we took that super seriously. Of course, we wanted to not just become zeroed in to just that one problem scenario.
Of course.
We wanted to figure out what other kinds of edge cases might come up, and how would ACAS-X resolve them compared to TCAS?
All right, great. I have more questions. I'm going to go, real quick. One of the questions is on optimization side of the things. So when you are doing this neural network verification, so what kind of optimization algorithms are you using? For example, are you using branch and bound techniques like integer programming and stuff like that, or other types of optimization?
Yeah, so branch and bound is definitely one of the key insights. If you take a look at this long survey article that we wrote with Chong Liu,
yes.
They've tried lots and lots of different kinds of approaches. Mixed integer programming formulations where we can just make a call out to Gurobi or something like that.
Yeah.
That's one kind of approach. There are, in order to really scale up, it requires a combination of a number of different insights.
All right, great.
But branch and bound is definitely one of them.
Definitely one of them. Nice. Okay, one other question is, do you see any other future areas other than aviation and driving that this research can be extended?
Great question. So actually, one day per week, I spend consulting as a senior advisor to BlackRock, which is actually the world's largest financial institution in terms of assets under management.
Wow.
And so they need to make decisions under uncertainty about, investments and how to manage financial resources. They want to reduce risk. So instead of, trajectories of aircraft, we have trajectories of, investment returns.
Nice.
And in aircraft, we want to avoid crashes. In the financial system, we also want to avoid crashes. And so that's one area. Another key area that I didn't mention here is medicine. So a POMDP is just a really lovely framework for modeling decision-making in medical contexts, right? You have the state of the individual, maybe that they have lymphoma or something else like that. The doctor has to make decisions about what information gathering actions to take. Maybe it's a PET or CT scan, maybe it's a biopsy or whatever. And it's actually really important to reason over an extended time horizon to come up with the best possible outcome under uncertainty for the patients. That's pretty key. One of the most exciting things about POMDPs.jl is, like I mentioned, making it accessible to non-experts. And so we have folks from various medical schools who are taking our tools, using them to make decisions about breast cancer screening and so forth. And it's just been great.
Nice. Okay, so those are the questions by the audience. If you have just 2 more minutes, I also want to ask some questions myself. One of the questions that I want to ask to you, Mykel, is so about this whole verification stuff, right? So that had been, around for years for both aircraft, automotive industry, but things weren't as complicated as neural networks back then, right? So maybe verifying some stuff was easier. And now we are in this strange age where we have this amazing technology, neural networks. They perform so well, but at the same time, they're also very difficult to verify. And right now, what we are doing is you and a lot of other researchers are trying to develop new methods so that we can satisfy this, guarantees the safety verification. But do you also start seeing some kind of shift in the industry, both aircraft and automotive, that do we need to change how we, look at verification and safety so that we can actually embrace these technologies better? Because every time whenever I do a project with industry or a consult with industry, they are always very concerned about that. Like, is it going to be safe? Is it going to be verified, etc.? So do you think they should also change some of their looks on how they should handle artificial intelligence technology, or their view is correct and we should adapt to them? So what do you think about this?
Yeah, I think actually both. As we were trying to get the ACAS system through the approval process, even that was challenging, and that did not involve neural networks at all. That it involved a large, lookup table. And lookup table. We tried to extend things a little bit at a time. We said, a lookup table is kind of like these data files for other avionics systems and so forth. We have to be very careful about this and gradually push the boundaries of what's accepted. We don't want to be too fast. I think what happened with the 737 Max 8 and Max 9 was they were a little bit too hasty in terms of the verification and validation. And we can't afford to have something like that. But I think people are starting to realize that the only way to do certain things is through a learning-based approach. You can't do computer vision very well using, you can't program the mapping from a video image to, bounding boxes. You can't code it. There's no other option. I can't imagine any other option than to train it from a lot of data. So if you want to fly these kinds of things, you need to come up with methods that allow for their verification and validation. But I think on the flip side, in industry, we can't kind of just take methods that people have been using for, non-safety critical systems and just expect them to work reliably for aircraft and cars. And so I think a number of companies are now thinking about ways to kind of constrain their design so that it's easier for validation.
Nice. Okay, I see. Yeah, great answer. Thank you. So then one final question might be, so I really like this adaptive stress testing idea because it can lead into some interesting insights, right? And I mean, in my view, that is one of the things that always gets me excited about artificial intelligence. It gives us something that we humans sometimes cannot think about. Similar to how AI can discover, for example, chess and Go strategies that we cannot think about. So can you maybe share an experience in this adaptive stress testing where you found a scenario, whether it's an aircraft or a driving scenario, where you were really surprised that, wow, I'm really glad that we discovered this edge case. Otherwise, maybe we couldn't even think about it. Do you have a story like that? Maybe. Yeah,
so we talk about an example of this in there was a longer journal article on adaptive stress testing where we showed some examples using ACAS-X and involved some complicated reversals. I couldn't have come up with that kind of scenario. Everything has to be like, the timing has to be exactly perfect. The accelerations by the pilots have to be exactly right in order to get this kind of failure.
But it can still happen, right? I mean, it is not super low probability.
Yeah, it's very low probability, which is great. But we want to kind of understand what those failures look like. In some cases, if you throw a supercomputer at it and it runs for 10 days and the failures it's producing are just so unlikely, and when we look at it, it's like, yeah, we don't really care about this particular scenario, then we can have a nice feeling in our heart that, we're on the right track. It's not proof that we're safe, right? But it gives an indication that we're on the right track.
Yeah, so I'm wondering, maybe can you come up with metrics of robustness, right? Because that is one thing that I really miss from old school control theory. We have like very well-defined mathematical techniques where we can say this system is robust to this amount of, things. So I'm really wondering, maybe with all these methods, we can come up with, robustness of systems with respect to these metrics. Okay. Mykel, thanks a lot for your time. I just want to finish this with a fun, anecdote. So we talked about PAM-DPs a lot, and you emphasized several times how, capable they are, how strong of a framework that is. So I want to share this with the audience. Last year, I actually visited Mykel at Stanford, and he actually gifted me a T-shirt. I don't have it with me right now. I really wanted to show it, but it is not with me. Do you have it? Nice.
I think
we should. One. Yeah, I want to show it. Yeah. Nice. So it says "Life is a PAM-DP." Nice slogan. So yeah. So I actually wore that several times, outside, and people saw that, and they are really confused. Life is a pump, like what is that? Is that like a misspelling? And then they ask me, and sometimes people with no technical background, they ask me, "What is a pump?" And I would say, "Oh, it's a partial observable Markov decision process." And they're like, what? Okay, so this can't be real. But sometimes I explain it to them when I'm motivated enough, and they are amazed by, wow, this sounds really cool. So nice T-shirt. because of this T-shirt now, several Turkish people knows what a PAM-DP is. So I wanted to share that. I wanted to share that with you. All right, Mykel, thanks a lot for your time. This was a great talk. We really liked hosting you. Hopefully, after all this craziness, the pandemic is truly over. We will be able to host you in Istanbul as well. We have got some amazing places to show you, and our campus is really beautiful. So hopefully next time this will be in person. Thanks a lot.
That's great. Thank you so much for the invitation.
No problem, and thanks a lot for the audience for the amazing questions. Thanks a lot, everyone.